Good evening, everybody. Can you hear me?
Yes, we can.
Thank you, madam. Good evening, everyone. We are ready to begin the second guest lecture of the annual lecture series organized by the Chemical Society of University of Peradeniya. As you have already been informed, today's lecture is based on the novel perspectives on brain disorders with microengineered electrochemical detection platforms, conducted by our guest speaker, Dr. Srimal Aminda Samaranayaka, who is a research scientist in Spark Therapeutics, Philadelphia, Pennsylvania. Let us directly move on to the procedures. It is my pleasure to welcome all of you to this fascinating lecture, which I am sure every one of you is going to find exciting and beneficial. First and foremost, I warmly welcome our guest speaker, Dr. Srimal Aminda Samaranayaka. Next, I would like to welcome Head of the Department of Chemistry, Professor Manavadevi Ganehenage, and the Senior Treasurer of the Chemical Society, Dr. Tiloka Aryasena, whose guidance and support has been an inspiration for us to organize this event. In addition, I would like to welcome the lecturers from the Department of Chemistry, lecturers from the other departments, demonstrators, and all the students who have joined us to benefit from this lecture. I'm confident you will find this lecture inspirational, exciting, and beneficial. Before proceeding to the lecture, I would like to invite Professor Manavadevi Ganehenage, the head of the Department of Chemistry and the patron of the Chemical Society, to share a few words with us.
Maybe 1 second. No, just video. Okay, thank you very much, Naveen, for the kind invitation. So I would like to just see the face of Dr. Srimal Samaranayaka. I'm sorry, Srimal Samaranayaka, after a long time. So it's a pleasure to just address you. Actually, this is the first address as the head of the department regarding the Chemical Society. And if I just brief what we are doing here in chemistry, so our main objective in our study program, just by giving a subject to our students to produce a graduate to be competent to contribute to the society. So in doing so, we try to give a sound knowledge on theory and application, just applications in industrial operations. At the same time, we want our students to improve their skills. So skills, if you just consider the management skills, communication skills, computational skills, presentation skills, and mainly the personal developments. So if you just consider the personal developments, so we need you to just improve your leadership qualities, social interactions, and team work activities. So you know that so when you just apply for certain jobs, and if you just go to do your PhDs in other countries, we have to provide recommendation letters to you. So if you look at those recommendation letters, most of the time they ask us to give us feedback about you related to your skills. So they never ask about your qualifications, paper qualifications. They want us to just give some statements regarding your leadership, the ability to work as a team, and those things, your soft skills mainly. So when we offer our program, so our program is designed to just give you a chance or opportunity to improve those skills. In addition to that, in our department, if any student who just follow chemistry as a subject, the student gets a chance to learn through the subject, and also there are many activities. So if you engage on all those activities, ultimately you can just improve your skills. So that the activities we just conduct through the ChemSoc or the Chemical Society are very important for you to improve those skills. So therefore, what I ask all the students who are here in the presentations today to become members of this chemical society and try to engage many activities as far as possible. And in that way, you can just improve your skills. So here you can see in this picture some of the opportunities that we provide students through the subject to improve their skills. So you can see here our emeritus professor, Professor H.N. B.M.R. Bandara, is just questioning the students. So we just give students to present their research in terms of posters, so probably maybe the presentations. And also we just provide students to do group activities. In the practical classes, we ask you to do some group work. And also we just want you to just develop your that leadership qualities. We ask one students to do the things and then discuss with the others. Likewise, we do certain things through the subjects. That's how you just improve your the skills there. So at the same time, if you are a member of the chemical society, so we just conduct many activities. By engaging to those activities, you can just improve your other soft skills. So in previous years, I have seen we invite some speakers. The guest speakers are invited, and then some seminars are done. Those days, I remember we had a magazine. There we give students a chance, and also the staff a chance to just express their views. So they write down, they just forward articles, and then sometimes students make poems, and then we just publish that magazine. But I didn't see that magazine very recently. In addition, our students just in the chemical society go to some schools, and then they do some activities with the students, some community activities. So those things are very just interesting, and also those activities help our students to develop their skills. So in doing so, what I recommend as the new head chemistry, you can continue some or you can add some more activities to the schedule. And then as such activities, webinars, you know that under this current pandemic, it's kind of difficult for us to invite people in person. So in order to solve that problem, as the treasurer, Dr. Tiloka, just attempted, we invited some speakers to do online lectures to our students. Through that, we can just give some feedback about what others are doing out there, how chemistry is just used for the development and for our future. And also, I am planning to have a series of frontiers in chemistry in future, so you can see those things. So it is a great pleasure to see now today speaker Dr. Srimal. I think he just graduated from our university in 2010, I guess. And then after that, I met him once when he visited Sri Lanka once. And I thought he was doing his PhD at the Wayne State, the same place where Dr. Tiloka and I got our PhDs. But I got to know today that you just left from Wayne State and then completed your PhD somewhere else. However, now you are a doctor, you got the degree, PhD degree from USA, and then qualified enough, and then now working as a senior scientist in a therapeutic company. So it is a very good pride for us, for our students. You are also chemistry special students graduated from our department, and we are very happy to just see you, and then welcome address will be given by Dr. Tiloka. So what I want our students now who are running this chemical society to tell, so we have many collaborators, local collaborators and foreign collaborators. As an example, if you consider Slingtech, Unilever, Hemas, IFS, so we can invite people working there as guest speakers, or we can send our students, no matter they are general students, environmental students, applied science students, special students, we can have collaborations with them, and then we can exchange our ideas. And also we have many connections with developed countries like Japan, USA, UK, Australia. So we have our alumni there studying their PhD. So we can just through webinars. So if they come to Sri Lanka, we can just have discussion. So therefore, I would like to request our the current membership, if there's a possibility, try to include some activities to provide opportunities for the students of our faculty to excel in their scientific journey by understanding and applying the key chemical principles and updating their knowledge with new trends and finding in the chemical world, and by improving their skills in leadership and teamwork and bringing out the hidden skills of students to explore their activities and assisting in planning higher studies and training for their future career. So when we invite people like scientists like Dr. Streamals, our students get the chance to discuss with them and then learn about how they get opportunities to go abroad and then continue their studies, and also to enhance creative thinking and the innovative solutions to solve the problems, and in this regard. So you can organize many activities. New activities are essential. So you can enhance the interest of the team participation. So we had some of the activities like chemical society activities, chemistry padura, and there we just everybody's just got together and then started singing, and sometimes we just have the some sports activities. So mostly only special students are, honor students are just doing these activities. I request everybody to be together when we are just organizing the activities in chemical society. And first thing I would like to ask you to launch a web page, and also I just went to your Facebook and then check the status, and that is not maintained in better quality, so you have to have a better Facebook. If you look at the chemical society web pages or Facebooks in the other universities, you will see how they maintain, so up-to-date information are there. And also try to publish the magazine annually, and also these are the suggestions. We can conduct inter-societal competitions such as debates. So we have the chemical society, botany department has a botany society. Likewise, we can have that kind of competitions, and also you can conduct some other competitions to just see the soft skills of the students, and we can ask the students to compose poems, we can ask them to do dances, singing, drama, drawings, and under this ChemSoft. And also we can give chances for students to present on emerging chemistry of the world. Now, after giving the presentations, by inviting the speakers, they learn how to make a presentation. Then we can ask the students, there are students who can just do a good presentation, especially our general students, they don't get a chance to do presentations. We can ask them to just select some interesting title related to the emerging chemistry, and then we can ask the students to organize a meeting or presentation or seminar series, and then we can let them a chance to present. So, and also we can have the entertainment events such as annual ChemSoft trips by joining academic staff members, temporary staff, and activities to enhance our social harmony. So as an example, so we can take the students to industries or some scientific institutions like Atomic Energy Authority and just the government analyst department. So this is given mostly for the special students. But my request is to just through the ChemSoft, we can take our general students also there, 1 or 2 day trips. So that will be very helpful for them to know about what people are doing out there related to chemistry, and then they can have network and connections. So my suggestion is to do activities to attract more members to our society and try to achieve the best out of best. So with that, I conclude my introduction, and then Dr. Tiloka will introduce Dr. Srimal. So I will be here to listen to Dr. Srimal. Thank you very much.
Thank you very much, madam. And then we appreciate your presence despite your very busy schedule. So thank you for all the suggestions. Now I would like to introduce, it's my actually pleasure to introduce Dr. Srimal Samranayake. Dr. Srimal graduated from University of Peradeniya from BSc Special Degree in Chemistry in 2010, and he obtained his PhD from University of South Carolina, Columbia in 2017. He worked as a graduate research scholar in the University of South Carolina from 2015 to 2017, and he has also worked as a postdoctoral fellow in the Vanderbilt University, Nashville, Tennessee, from 2017 to 2020. He is currently working as a research scientist in Spark Therapeutics, Philadelphia, Pennsylvania, USA. He is also a reviewer in Frontiers in Pharmacology and Analyst Journal, and he has received a number of awards, including Graduate Fellowship Award from University of South Carolina. With that, I would like to invite Dr. Srimal Samaranayake to deliver this lecture. Over to you, Srimal.
Thank you, Dr. Tiloko and Dr. Manamadevi for the kind introduction. And it's a great pleasure to present in front of the young crowd of the ChemSoc, because as Manamadevi might have mentioned that I was a member too back then, and we learned a lot, and we learned a lot of soft skills and leadership skills during those times. So could you please confirm whether you can hear me and see the screen well?
We can hear you, Srimal.
Okay, great. Today, I'm going to talk about the research work that I have done during my PhD work at University of South Carolina and Wayne State University in the Hashemi lab. So where we developed micro-engineered electrochemical detection platforms to monitor and study neurotransmissions in the brain, so we can have novel perspectives on the brain disorders. So let's get into the details. So the big problem we want to answer throughout our research is the depression. It is a mental health disorder characterized by persistently depressed mood, loss of interest in activities, which could significantly impair in daily life. The persistent feeling of sadness, hopelessness, stress, pain, could end up with also associated with the thoughts of suicide. I'm pretty sure every one of you at least heard about a sad story that someone end up with a suicide because of depression. And the numbers, depression by the numbers are pretty significant. So these numbers are before COVID, but in 2017, WHO announced that depression is the leading cause of ill health worldwide, more than 300 million people suffering from this disease. And the numbers are in US still the same and rising. Depression is the leading cause of disability, and more than 17 million people suffering from depression. So this together is a huge social and economical burden to individual countries as well as to the whole world. So do we know why depression is a brain disorder? What are the underlying chemical mechanisms, neurochemical mechanisms? The monoamine hypothesis was proposed in late 1970s, which shows that serotonin, a neurotransmitter, is low during depression. So serotonin is a neurotransmitter which regulates mood, appetite, sleep, and emotions, and found to be low in the brain. So if you think about when you stress or depressed, your mood is upset, and you have a bad appetite, you can eat ice cream, sweets, or you can't eat anything at all. So the sleep is the same. So either you sleep more or you don't sleep at all. So the emotion is variable too. So it's true that serotonin is highly involved in the brain disorders. So the idea was that serotonin neurotransmission is lower during the depressions if you have therapeutic approach which can increase the serotonin levels in the brain. So that could be beneficial to get rid of these phenotypes during depressions. Along this line, so several medication has been have been approved from the FDA, and these are the graph representing the efficacies of these drugs. So vertical line along the one represents the placebo effect or the control. If the drugs have significantly higher efficacy with respect to the placebo effects, considered as active drug. So these are the frontline medications currently used for the use as antidepressant for to treat depression. And as you can see, these drugs are barely 2 times better than the placebo effect and have a very huge variable efficacy. So it's been roughly more than 30 years, and still these are the frontline medication which were synthesized or produced depending on this monoamine hypothesis. But along with that, this variable and low efficacy, there are other questions that it is for depression, because it is difficult to diagnose. If you think about a peripheral disease like diabetes, you will go to your physician, and they will ask for your blood, urine, and they know what biomarkers to look at exactly, and there are chemical tests to do that. But when it comes to the psychiatric or mood disorders like depression, it's extremely hard to detect these neurochemicals, because we don't know, simply we don't know what neurochemicals we need to detect in order to detect depression. So simply what happens, if you go to a doctor, they will ask a bunch of questions: how you feel, whether you have suicidal thoughts, etc. So depending on how you answer them, they will prescribe with drugs. So the question is why we have a lower efficacy of drugs, why we don't know about these chemical messengers in the brain, and why we don't know these underlying neurochemical mechanisms of neurological disorders is because simply it's very difficult to monitor or study neurotransmissions in the brain, because the existing analytical methods do not facilitate the temporal resolution we need in the millisecond scale. It does not facilitate the selectivity we need, or the sensitivity, or the spatial resolution. So without these techniques, it's hard to study these brain disorders or to produce novel therapeutic approaches for this. So our research was want to give a new proposed hypothesis for the depression or serotonin related diseases. And we already know that serotonin is related to the brain disorders, especially for the depression. But serotonin is not alone in the brain. There are many other neurotransmitters, neurochemical mechanisms in the brain. So one other neurotransmitter that we were interested in is histamine. Histamine is a neurotransmitter as well as a neuromodulator. That's why it can regulate serotonin in the brain, but also histamine can regulate sleep, inflammation in your body. So a quick example is that if you have an allergic reaction, so the pill that you always take is antihistamine pill that reduce the histamine levels in the peripheral system, which reduce the inflammation. So histamine also a key biomarker in neuroinflammation, and a neurotransmitter. So we thought histamine might regulate serotonin in the brain, and maybe there is a connection to the depression. So that's what we want to find out. And if there is an effect, how does it going to affect to the therapeutics we already have? So our approach is going to be using a electroanalytical method. So in the brain, so there are a lot of thousands, millions of neurons. Whatever you think, whatever you do, whatever you feel, it's all because of these neurons talks to each other, connects to each other, propagate signal from one to another to make it happen. But these neurons are not physically connected to each other. They are separate. So then how these neurons propagate the signal one to another? That's through small chemical messengers called neurotransmitters. The serotonin that we talked about earlier, that is comorbid with depression, is one of the neurotransmitters, but there are many other neurotransmitters like dopamine, serotonin, histamine, GABA, acetylcholine, etc. So what happens? So during an impulse, presynaptic neuron releases neurotransmitters to the synaptic space, ultimately activate a postsynaptic receptors. This activation leads to open up several ion-gated channels, which release or propagate another signal through the postsynaptic neuron. in most of the time, the histamine neuron will release histamine neurotransmitter and activate a histamine postsynaptic neuron. But sometimes this histamine can activate other types of neurotransmissions, neurons like serotonin that can regulate that particular mechanism too. So that's what we wanted to study, how histamine regulates serotonin neurotransmissions in the brain. So how we're going to do it is using an electrochemical platform. So we position an electrode into the brain, which can detect these neurotransmissions as long as they are electroactive. So we use fast scan cyclic voltammetry. So those who already start in the 4th year, I think they are still have that course from, we learned it from Dr. Amal Priyantha, sir, but so it's kind of pretty much same, the classical cyclic voltammetry, but we use much higher scan rate and a much higher frequency in order to achieve the temporal resolution we need. So we use a waveform. So let's go through with this using the serotonin waveform. So this is selectively modified to detect serotonin. So this is a serotonin molecule, and in between it's oxidized and reduced form. So the waveform is a set of instruction in terms of potential to the electrode to selectively detect particular aniline. In this case, it's serotonin. So we hold the electrode at 0.2 potential and then ramp up to the positive potential. And that positive potential will oxidize the serotonin molecule, end up with giving our oxidation peak in the cyclic voltammogram, and it will ramp back to the negative potential and the holding potential. So that will give the reduction potential. The shape of the cyclic voltammogram, the oxidation peak, the reduction peak, and used to selectively identify the. In our technique, fast scan cyclic voltammetry, collect these cyclic voltammograms and open up along the voltage axis so they have the oxidation peaks here. Instead of coming back, it will open up. You will see the reduction peak. Then the cyclic voltammograms will be collected over time for a 30-second period most of the time, and then you can make a 3D plot. The oxidation peaks will come out of the page, and the reduction peak will go into the page. And here we assign the positive currents. The currents coming above the page is in green, and the current goes into the page in blue. The bird eye view of this plot will represent here as the color plot. The y-axis represents the time, x-axis represents the voltage. So this is the output we always get from our technique. So one important thing I want to show you is that since we are using much higher scan rate and frequency, we do not give enough time to the system to get rid of the charging. So that is one of the potential drawback in this technique. And so those who invented this technique use background subtraction in order to get rid of the charging current. So the idea is the very first few cyclic voltammograms considered as the background, and rest of the cyclic voltammogram collected after that will be mathematically subtracted from the background cyclic. So then each and every cyclic voltammogram will be background subtracted, and ideally, if there is no change in the system, you would not see anything, like it will be just brown color. So because of that, we introduce a stimulation, electrical stimulation to the brain that could release particular neurotransmitter if you need. So that change will give us, that electrical stimulation will give a change in the neurotransmission, which is represent an event here. So once you have the color plot, we can extract the data out of it. So if you take the vertical strip along the line, it will represent the cyclic voltammogram, can be used for the qualitative identification. We take the horizontal strip along the event, that gives you a current versus time curve. So this is one of the most important data out of this this technique, and I'm going to show you a bunch of curves like this. So therefore, I would love to take some time and explain what does this mean. So the very first part of this curve will represent as 0, but it is not 0 because it's the basal level. Because in the brain, there is always some neurotransmitters released and reuptake. So this amount will be subtracted out of the background subtraction. So therefore it will be look like 0, but it is actually the basal level. So then during the stimulation, there will be more neurotransmitters and the synaptic spaces that will oxidize more neurotransmitters, end up with giving a more current. And during the stimulation period, and then after the stimulation, these neurotransmitters will go back to the cell or degrade, so that will reduce the extracellular concentration. So the current will drop to back into the basal level. So this curve is current versus time, but you can use this electrode and calibrate the electrode using an in vitro experiment. Then you can convert this current into the concentration. So once again, so just the summary of this part is that this is the basal, and this part of the curve represents the release, and this part of the curve represents the reuptake of new transmissions back to the cells. So, and this is a real life image of the stimulation electrode. It's small here, and this is the carbon fiber micro electrodes. We made it in our lab, and it's hard to see here from the naked eye, but the tip is somewhere here. And this is this in the background. You can see the stereo tags instrument that hold the mice for the during the experiment. So during the experiment, we position the electrode. So this is a sagittal section of a mouse brain, which goes along the nose towards the tail. So this side should be the nose, this side would be the tail, and the working electrode can be positioned to the place of interest. So in here, it's to detect the serotonin, and this is the CA2 region in the hippocampus. We position the stimulation electrode to the medial forebrain bundle. So this bundle contains all types of neurons. If you stimulate, that electrical stimulation propagates through the neurons and release neurotransmitters at the CA2 region. So next, I'm going to show you a video that how it look like when it's actually collect the data. So this is a color plot. So this will be propagate as it's collecting, and this will show the current versus time that I showed you earlier, and this will show the cyclic organogram as it collects. So up to 5 seconds you won't see anything, but at 5 seconds you see the stimulation. So this is the release of serotonin, and if we take the vertical strip along this event, it shows over here the current was pretty much low, and during the stimulation it's released and then drop back to the basal level over the time. So this is a real-time in vivo serotonin detection in a mouse. And for our experiment, so if you remember that I told you that I wanted to study how histamine regulates serotonin in the brain. So it would be beneficial if I can develop a method to detect both histamine and serotonin. So then I can study how histamine regulates serotonin in the brain. So these, again, the parameters that I can change in the waveform, so I can make it more selective and sensitive to detect both of these neurotransmitters at once. So the holding, I can change the holding potential, maximum potential, the minimum potential, and the scan rate. So after a bunch of in vitro experiments, so this is the waveform that I came up to selectively detect both histamine and serotonin. So that's the in vitro part. So the more difficult part is the in vivo. So because you need to find a place in the brain which has both histamine and serotonin. So then I can study how histamine regulates serotonin. And the next part is we use a stimulation electrode, but this stimulation needs to stimulate just histamine, but not serotonin. So then I can study how the electrically evoked histamine levels affect on the serotonin system in the brain. So after half a year worth of experiments, systematic experiments, we came up with this animal model to detect histaminogenic regulation of serotonin in the brain. So this is once again the sagittal section of a mouse brain. The working electrode is positioned to the posterior hypothalamus, where it has innervation of both histamine and serotonin, and the stimulation electrode is positioned to the medial forebrain bundle just to stimulate histamine but not serotonin. And this is the color plot that you would get when you do this experiment. So this histamine release event happens over here, and if you take the vertical strip along the histamine, which represents by HA, is shows here in the solid line. And the in vitro experiment or the bench experiment shows in the dotted line. As you can see, the oxidation peaks around the same, around 0.3 volts, which shows that it is histamine. The shape of the cyclic photomograms are different because it's extremely hard to reproduce the in vivo the environment in the bench. And next is the serotonin event. So it's appeared to be in the blue color, in the blue color as a negative color, and that's not what we expected first, because we expect, so once you stimulate, you would expect to release neurotransmitters of serotonin too. So before we try to think about what is this, we quickly did another experiment. We moved the electrode to the substantial nigra. So that's a place we are sure about that serotonin is released. And we use the same waveform, this same novel waveform for the histamogenic regulation of serotonin, and we stimulate, and we did see a release of serotonin here. But we did not see a release in our experiments, So let me explain what's going on. So this is once again due to the background subtraction that I explained earlier. So in this condition, so this represents the serotonin levels. This is 0. This is somewhere at the basal, and then during the stimulation, the serotonin levels raised up. And but when you back down subtract, then this will subtract by the basal, so this will drop back to the 0. And this stimulation value will be subtract from the basal value, so then it will give you some kind of a value here. So then you will see an increase in a current or a positive current in the system. But what happens if the serotonin levels goes down or depleted with respect to the basal level after the stimulation? So like here, so this is the basal level, because of for some reason that the serotonin levels goes down. This is not 0, but it is a lower level with respect to the basal level. The mathematical background subtraction, the subtraction of this by this, will give you a negative value in terms of the mathematical value. So that's why this serotonin event appears as a negative value, even though it's serotonin. This does not represent that serotonin levels go beyond 0. It just shows that the serotonin levels drops with respect to the basal value. And then I would love to show you once again a video of how it looked like when it's collect in real life. So once again, up to 5 seconds, you won't see anything. And here we stimulate. So this is the release of histamine. And after a little bit time, you will start seeing the serotonin depletion here. And then over time, it will come back to its basal levels. If we take the horizontal strip along the histamine event, it will show over here. This is the release of histamine. This is a reuptake of histamine back to the cells. So this is the first time that we did see the simultaneous detection of histamine and serotonin in mouse posterior hypothalamus. So let's see what's going on. So if you take the horizontal strip along histamine, it will reproduce the current changes for the histamine event, and using a calibration curve, you can convert into the concentration. So this axis represents the change of histamine and change of serotonin, but once again, this represents the basal level. During the stimulation, histamine level released, and then after the stimulation, it will come back to the basal levels. Notice the concentration is in micromolar range. The serotonin levels are start depleting a little bit after the histamine release. It should be because according to our hypothesis, the histamine need to be there in order to inhibit, deplete the serotonin levels in the brain, and it's inhibit up to roughly to 40 nanomolar range, and then over time it come back to the basal level. So the question is, why serotonin levels deplete in the presence of histamine? So after several literature searches and several pharmacological experiments, we found out that happens because of the H3 autoreceptors. So these H3 autoreceptors are typically found in the histamine presynaptic neurons. And once histamine neuron release neurotranshistamine to the synaptic spaces, and once the synaptic space have enough histamine, the one of the histamines will come out of it and activate one of these H3 receptors. So these H3 autoreceptors act as a feedback mechanism to the histamine neuron, and once you activate it, so this receptor tell to the histamine neurons, hey, histamine, so we have enough histamine in the synaptic space, don't release any more histamine. So that reduces the histamine release to the synaptic space. So that's kind of a feedback mechanism to control these histamine levels in the brain. But these H3 receptors also found in the serotonin neurons. So these once there is a high amount of histamine levels in the synaptic space, this histamine will activate H receptors on the serotonin neurons and send the same signal, hey, serotonin, so we have enough histamine, don't release any more serotonin. So that will reduce the release of serotonin to the synaptic spaces, will ultimately lead to the lower serotonin levels in the brain. So that's why you would see the depletion of serotonin levels over time after this release of histamine. So then we want to make sure that this depletion of serotonin happens just because of histamine, not due to any other reasons. So we change the release of histamine by changing the stimulation parameters. We can change the stimulation frequency, pulse width, and the amplitude. And we change it in the different parameters for the histamine, and we see what happened to the serotonin inhibition or the depletion. So in each curve, the lighter curve shows the lowest parameter, and the brighter curve shows the dark curve shows the highest parameter. Let's look at the stimulation pulse width curve just to understand the story. So let's look at this. The lowest one shows here, and it's a very small amplitude, and it's also followed by a very small inhibition of serotonin levels. If you look at the highest release of histamine, followed by the highest inhibition of serotonin, and this is true for the all three parameters that I show here. Okay, then we made a correlation plot between the released histamine in the x-axis and the inhibited serotonin in the y-axis, and as you can see, it's a strongly correlated, which suggests that histamine inversely regulates serotonin levels in the brain through H receptors. So we were quite happy about this finding, and then we went ahead and collaborated with mathematicians in Duke University and the Ohio State University to develop a mathematical model for this data. So this is much more similar to the rate equations that you would learn in your undergraduate level. So let's look at the histamine, the mathematical model. So the left part just simply represents the extracellular concentration of histamine over time, and it's governed by the several factors. The release of neurotransmitters is definitely a plus value for the extracellular concentration. This is the reuptake into the terminal, so that is a negative factor. And if there is any leakage when it's reuptake, so that will go back to the extracellular concentration, so that why it became a positive contribution to the this equation, and the reuptake to the glial cells and the leakage from the glial cells is a negative contribution to this equation. So this is one of the simplest version of the equation. So we wanted to start with having the hope to develop it in the future. So the one important thing we wanted to contribute is that this H3 autoreceptor function that regulate the release of histamine in the brain. So this is in the bottom, you can see the similar equation for the serotonin, and as the similar functions, the release, reuptake to the terminal, and leakage, and reuptake and leakage from the glial cells. And again, we incorporate the autoreceptive function to the release function because we wanted to test that. Then we wanted to test our mathematical model, whether does it behave as we expect. So for that, we did a pharmacological experiment. Let's look at the left two graphs. So once again, the blue represents the control histamine release after the stimulation and reuptake back to the cell over time. And this is the corresponding serotonin inhibition shows in the magenta color. So then we use a drug called thiopyramide. So thiopyramide is H3 receptor antagonist. So that means it negatively regulate the H3 receptors. So simply, if histamine bind to here, and histamine will send, don't release any more histamine, but thiopyramide will send a signal to the histamine, hey, histamine, release more histamine. So then this will release more histamine. In viewer experiment, you would see that more release of histamine over time. So then if you look at the serotonin, the corresponding serotonin, you would see the more inhibition of serotonin because of the more inhibition, more release of histamine. Once again, this is also aligned with our theory, more histamine, more inhibition of serotonin. And in order to test our mathematical model, first, we used our control data to develop the mathematical model. And as you can see, this dotted line, these dots represents the mathematical model. It's fit perfectly because it should. That's because this is the data we used to develop the mathematical model. And then in the post-drug condition, we only changed this autoreceptive function in both equation, not any other functions in the equation. Then we came up, then we did able to fit the model into the data, as you can see in the dots in the green and the orange curves here. So this proves two things: that one, that our mathematical model works, and our hypothesis is true that histamine inversely regulates serotonin in the brain through H3 receptors. Okay, so this is where we start. We knew that serotonin regulates depressed brain disorders during depression. We thought maybe histamine have something to do with serotonin, and our experiment suggested that histamine inversely regulate serotonin through H3 receptors. But now we need to find a link between histamine and brain disorders in general to complete this circle. So one of the easiest way is the neuroinflammation, because we already know that histamine is a key biomarker in the peripheral system, and histamine levels are higher during inflammation. So we wanted to test whether this is true in terms of neuroinflammation, so then we can connect this story. So our hypothesis is that in normal conditions, in healthy conditions, that histamine will release and it will inhibit some amount of serotonin, and it will lower the serotonin levels in the brain. But as long as this is in an equilibrium, it's fine. But during the neuroinflammation, we assume that there's more histamine levels in the brain, so that will inhibit more serotonin in return. So we wanted to test this hypothesis, and when we were doing these experiments, we collaborate with Dr. Boo's lab from the University of South Carolina. So they had these HIV transgenic rat animals. So these animals have the same type, all types of phenotypes of the disease, but they cannot propagate the disease from one to another. So therefore it's a great animal model to study HIV transgenic rats. But we were interested about this animal model because these animals shows a increased pro-inflammatory cytokine levels in the brain. So INF gamma, TNF alpha, and IL beta. So this suggests that these animals suffering from the neuroinflammation. So since we were doing experiment with these animals anyway, this became an excellent opportunity for us to study how histamine regulates serotonin levels in these animals during the neuroinflammation. So we performed the same experiment. So this is a sagittal section of the rat brain, the nose on this side, and the tail would be in this side. And we position the working electrode to the posterior hypothalamus area and use the same stimulation parameters and the coordinates to detect histamogenic regulation of serotonin. So as we expected, the left color plot shows for the control and the right color plot shows for the HIV transgenic rat. And this is the histamine event, and this is the histamine event for the HIV transgenic rat. Looking at the color plot, you can see there is more release in the histamine, And this is the average of 7 animals. Blue represents the control group and red represents the HIV transgenic rat. As we expected, there is more release of histamine during these HIV transgenic rat. We assume that it is because of the neuroinflammation. And so more histamine should inhibit more serotonin. And to check out that, we extract the data point along the serotonin event in both control and HIV transgenic rat, and it shows in the bottom graph here. Blue represents the control and red represents the disease mice, which shows that more inhibition of serotonin. This is not significant because of the high error bars, but it shows the trend. So once again, we confirm our hypothesis, the during inflammation, more histamine release and probably more serotonin inhibition along with that. Because of this not significance in the inhibition, we wanted to test just the serotonin signal and see whether it's give us any different parameters for that. So for this, we move the electrode to a place, we keep the electrode in the serotonin in the same place, and we move the stimulation electrode to the different place just to stimulate serotonin, and we use the serotonin selective waveform just to detect serotonin in the brain. So this is the serotonin event, and this is the serotonin event for the HIV transgenic rat. If you take the horizontal strip, the data along this event, it represents here. Out of 10 animals, the blue represents the control group and red represents the HIV transgenic rat. So as we expect, there is a lot of things change in the this disease animal. So let's look at into that deep. So these are the same curve that I showed you earlier. So this is, if you remember the things that I showed you about these curves, so this is a good time to refresh it again. So the one difference that you would see is the amplitude of release. So the control has a high release, whereas the HIV transgenic rat have much lower release. So if you think about, we never did this, but if you think about the mathematical model, so the release always contribute in this release term here, so that we propose that this release, the decrease of release, is due to the effect of H2 receptors by high histamine levels in the brain. And one other thing that you would see is the rate of release. So for the rate of release for the control rat is much higher, and the with respect to the rate of release for the control animals. So the rate of release again controlled in this release term here, and we assume that it is affected by the H2 receptors. And one other thing that you would see a difference is that the rate of free uptake. So because the rate of reuptake for the control animals are much faster, but the rate of reuptake for the disease animal is much slower. So these are the difference that we can show, that we can see using this technology. Earlier, so we never had this kind of technology to see these neurochemical changes, but now we have, and we did able to incorporate it to the mathematical models, so to get much more information out of it. So in the future, what we want to do is develop these mathematical models, incorporate all the possible biological function in it, and then evaluate the differences of these curves using this mathematical model. In simple terms, that this mathematical model will tell us, okay, in this is animal, this is HIV transgenic animals, the rate of release is different from this much because of the H2 receptor function. So that's the future that we wanted to go forward. Okay, for now, we know that the brain disorders, not specifically the depression, but it's cause the neuroinflammation that increase the histamine release and inversely regulate serotonin through H2 receptors. So, but if you look at the literature, you always say that the depression also comorbid with neuroinflammation. So maybe this is one of the reasons why serotonin levels are lower during depression. Is because of the neuroinflammation. So after that, we wanted to study some other things, that is the histamine reuptake mechanism. So in general, that each neuron dopamine has their own transporter to reuptake dopamine back into the cells, and serotonin has its own, but histamine does not have its own reuptake mechanism. So we wanted to study how histamine will reuptake back to their own cells. So to do that, we did a simple experiment. The blue curve shows the control, so before giving any drug. So it shows the release here and the reuptake back to the cells. Then we injected each of these animals from a particular transporter inhibitor. In this case, it's a GBR drug, so that inhibit the dopamine transport. So now in this case, we are just looking for the reuptake curve here. So if this drug able to inhibit the histamine reuptake mechanism, the rate of reuptake should be much slower. So we would expect to somewhere here. But for the dopamine transporter, it did not show any difference. That means histamine is not reuptaken by dopamine. So then we gave selective serotonin reuptake inhibitors, escitalopram and citalopram. And interestingly, we did show a slower reuptake in both cases. This became really interesting for us because these two drugs are frontline medication for the depression, which is supposed to increase the serotonin levels in the brain, but it's looked like for some reason it's inhibit the histamine levels in the brain too. So first we thought it may be okay, maybe selective serotonin transporters are responsible reuptake histamine. So when you use this drug, inhibit. But keeping that in mind, we use the citrulline and desipramine. These are norepinephrine transporter inhibitors, but we did observe the same thing, kind of slower down the reuptake mechanism. So that kind of showed us, so this is not probably the serotonin transporters, but all these drugs have selectivity towards organic cation transporter. That's a kind of a general transporter that can upregulate all types of neurotransmitters. So this is the dicenium-22. It is an organic cation transporter inhibitor. And when you inject that, you can see that it significantly inhibits the reuptake mechanism. Since we were really interested about these selective serotonin reuptake inhibitors because it's related to the depression, so we did these additional experiments to make sure that with the serotonin transporters reuptake histamine or not. So we use a transgenic animal model. So this is a wild type animal. So this is the serotonin transporter. So under normal condition, this serotonin will reuptake back into the cell, transport back into the cell. In wild type condition, when we give the escitalopram, which shows in this star, that will close this transporter. So the serotonin cannot get into these cells. So then it will be lay around the synaptic spaces. So you will see a huge increase in the serotonin levels in the brain. So that's the therapeutic idea of using these selective serotonin reuptake inhibitors as antidepressant drugs to raise the serotonin levels in the brain. But if you use this transgenic animal, MET172, so these proteins were engineered to not detect the selective serotonin reuptake inhibitors. So even if you give the escitalopram, this will not activate. So the transporter will be still open. The serotonin will be transported back into the cells. So in this animal model, you would not see any difference with the serotonin signal as you see here. So now we wanted to use this animal model to test the histamine reuptake mechanism. So if we obtain a similar pattern like this, that means, yes, that serotonin transporters reuptake histamine back to the cells. But if we see a different pattern, that means probably some other transporter reuptake histamine. So this is this data shown here. So once again, this is the wild type animals. There is no difference. So the control shows in blue color and the post-drug curve shows in the green color. We can see the slower reuptake mechanism as we saw in the previous slide. And even in the transgenic animal, escitalopram did able to inhibit the histamine reuptake mechanisms that suggests that serotonin nothing to do with the histamine reuptake mechanism, most probably this escitalopram has some selectivity towards the organic cation transporters that we found later to inhibit the reuptake mechanism. Okay. So now the story became more interesting because that involved the SSRI to the system. So let me explain. So our next hypothesis. Those who have depression, they will prescribe from antidepressant drugs, mainly selective serotonin reuptake inhibitors like escitalopram, citalopram. So the direct effect of SSRI increases serotonin levels in the brain, and that what it should do, and the increasing of serotonin levels will reduce the phenotypes of depression. So that's great. But according to the new data that we just found out, that this SSRI also inhibit the histamine reuptake mechanism through organic cation transporters and raise the histamine levels in the brain. And the higher histamine levels inversely regulate serotonin in the brain, inversely regulate serotonin and lower the serotonin levels in the brain. So now, according to this hypothesis, there are two factors controlling the serotonin levels. The SSRIs, antidepressants, increase the serotonin, and the indirect effect of SSRIs lower the serotonin levels in the brain. So we propose that this may be one of the reasons why these drugs are less efficacious and variable. So in order to prove that idea, so we did another experiment. So here we used a different technique. So in here we detect the basal level of particular neurotransmitter, not the stimulated level. The stimulated level shows over here. Okay, let me explain the data. So the blue represents the control group. So these animals, we measured the basal serotonin levels over time for this control group. And here we injected the saline, and we should not see anything because of the saline. And at 60 minutes, we injected it with SSRIs. So when you inject SSRIs, we expect it to increase serotonin because it inhibits the serotonin transporter that inhibit the reuptaking of serotonin back into the cell. So you would see increase of serotonin over time to 120 minutes. So then we have the disease phenotype. So in here, so we have the same different group of animals. We test we detect the basal level, and in this point, we inject the LPS. The LPS is a lipopolysaccharide that's commonly known agent to induce the neuroinflammation in the brain. If you remember, in our HIV transgenic rat experiments, we knew that the neuroinflammation raised the histamine levels in the brain and lowered the serotonin levels because of the H receptor inhibition. So as we expect, over time of when it comes to the 60 minutes, you would see the serotonin levels goes down because of the neuroinflammation. And then we inject the escitalopram to these animals, and you can see the rate of increase of serotonin levels is much lower with respect to the rate of increase of serotonin for the control group. So so this model is much more closer to the depression model. So the idea is that during depression, there is neuroinflammation, and it will raise the histamine levels in the brain, so which will inhibit the serotonin levels. So in return, so if you take SSRI or antidepressant drug when you have depression with high histamine levels, the efficacy of these drugs will not be as much as high for the wild type group. So in order to prove this hypothesis, this whole thing happens because of histamine. We add another animal group to the experiment. So once again, the blue represents the control group, and the red represents the LPS escitalopram group that I explained earlier. And we add another group which shows in the purple color. So once again, nothing happens up to 30 minutes, and then we inject LPS because of the neuroinflammation. There is high histamine levels, followed by inhibition of serotonin, which would see a depletion of serotonin levels in the brain up to 60 minutes. And up to this point, what we have is we have histamine, and we have inhibition of serotonin. And then if we just give SSRI, so the SSRI will increase serotonin levels in the brain, and at the same time, it will increase the histamine to some point, and this overall, this will inhibit serotonin again. So the rate of increase of histamine, serotonin will be much slower. But at the same time, we give another drug called FMH. So the FMH is a histamine synthesis inhibitor. So that shut down the histamine synthesis in these animals. So it's basically, it's take out this histamine term out of the equation. So which remains that just the serotonin and SSRI in the system, in the equation. So that means there is no inhibition because of the histamine. We should see a huge increase of the serotonin as we expected. So after 80 minutes, you can see slowly taking up, and after 100 minutes, you can see that serotonin levels ramp up to much more similar levels to the wild type or the control group. So that's really that proves our hypothesis. So the idea is that that may be true, because if you see, if you remember the efficacy drug, the efficacy of the drug that I showed you at the very beginning, they have the much variable efficacy. If it's because of histamines, it could be variable because the inflammation system is through your genes. So if the inflammation system is much more different from one person to another because of it's regulated through your genes, and that may be why these drugs have a variable efficacy as well as low efficacy because of SSRI. So our future plan is, or the suggestion from our research to the community is that we need to develop drugs which do not target that histamine pathway, so there is no indirect effect on the serotonin. So then drugs will directly increase the serotonin levels in the brain, so which will be much more efficacious and less variable in term as a therapeutic approach for the depression. And from that point, I would like to conclude my presentation. I would like to thank my PI, Dr. Parasto Hashemi, and my dissertation committee, collaborators, and all the members in the Hashemi lab. And this is an old slide, but all of these fellows are graduated from their PhDs now. And I would like to thank this opportunity to Tiloka, as well as the organizing committee of the CAMSOC to giving me this opportunity. And it's been a great pleasure and honor to present in front of you guys. Thank you very much. And if you have any questions, I am happy to answer any of the questions.
Hello, Srimal. Can you hear me?
Yes, madam.
Very glad to see you and hear about your very interesting and very important research. So this depression, anybody can get, right?
Yeah, so one of the animal models we try is that just chronic animal model. So we just introduce them a kind of a uncomfortable thing every day. Just, you know, no food, no something, and that could happen to us too, that any uncomfortable thing happen to every day for us that could lead for depression.
Yeah, is there any test, normal, simple test to check whether a person is near to depression, getting depression or depressed? In USA, are there any tests? No.
No, so that's what we're trying at the end. We wanted to develop models, tests. So one of the ideas we are having is that, because the method that I explained is not approved for a human to use in humans. So one of the approaches we want to do is just relate the brain chemicals to the peripheral system, because serotonin levels also found in the gut. So that's why when you have depression, you would have the, you know, the appetite, the dysregulation. So one of the approaches to see what happened to the serotonin levels in the peripheral system, and if there is a relationship, we can use it as a test, but it's not developed yet.
So can it change the serotonin level if there's something else also in the brain? For example, brain aneurysm or something?
Yeah, it could.
Could try it.
Yeah.
Okay, okay. So both levels, histamine and
Yeah.
serotonin.
So the neuroinflammation is kind of comorbid with all types of brain disorders. It's there for anything.
Mhm.
And so if histamine is there, it could change the serotonin levels too. So it's all connected to each other. So we try to sort out one by one, but probably there are many other factors regulate serotonin too.
Yeah, yeah. Okay, okay. Thank you.
Thank you. Thank you, madam.
So, Srimal,
Yes, madam.
so it was really interesting, but kind of advanced for our students, I think. And because you just explained the things related to your PhD research, I think, right?
Yeah.
So anyway, so that there are things that our students can learn from that. So I have a very small question. So if some patients just taking drugs to control or subside this depression, so I have seen that we know that there are some students among us also taking some drugs. So prolonged usage of the drugs cause some different other issues. So, have you come across that? And is it possible for us to just tell to continue uh, this kind of antidepressant drugs?
Uh, it's well known that there are many side effects of this antidepressant drugs, because as I explained, these drugs were developed because of these monoamine hypotheses found in 1970s, and that's so these drugs also have the selectivity to other transporters, other receptors, which regulate other neurotransmitters too. I mean, I cannot say about anything about it because it's drug related things, but there are studies going on with these drugs, so probably in the near future these drugs will be changed and we'll have more selective drugs for the just targeting serotonin system in the future. So right now there are side effects and it's well aware. So what you usually do is that physicians will prescribe the drug and then ask them to take for a couple of weeks. If you have any adverse effect, they will change it to another one and then ask them to take it again.
Okay, so that among the audience, most of our special students are there. So there may be some general students as well. So what kind of message you can just give to those students? So general message, not mainly chemistry, but probably it is related to the higher studies in USA, or just about the life that you are having in the USA, or just the students' future. Mainly, if a student is taking chemistry as a subject, so what kind of message you can give to the students?
Yes, it's a great opportunity to come to the US for me particularly, but so now there are many opportunities. I know many, even from our classmates as well as junior classmates, that they go to other countries too. So if you really if you really have the passion to study and engage with research and to find novel things, I'm really encouraged to go to the for a PhDs. So even for the general student, there is no limitation for that. So if you won't really do it, so you can go for a master's degree, and then it's kind of the same time period that you will spend for the special degree and if you stay for the demonstrator. So if you really want to do that, you can just go through that part. And the PhD is not just doing research, it's mostly the troubleshooting. So if you did research and if you do experiment and it worked first time, it's great, but most of the time it will not. So you have to do it again and again, and you need to read and you need to build your critical thinking and the troubleshooting. So that's one thing that I would encourage you to take the opportunity of your PIs, your professors, when you're doing your undergraduate research. So just try to think possible questions that you would have in your research, and then try to think how to solve that question. Even in the general research. In terms of life, US is great. I'm pretty sure all other countries are great too. So typical PhD will last for 4 to 5 years, but some last for the couple of years, and then you have an opportunity to do a postdoc if you want. So that's another couple of years that you can gain more experience in whatever the area that you have. So for me, so my PhD is mostly in chemistry, which related to electrochemistry, analytical, and neurochemistry. But my postdoc is mostly the biochemistry and molecular biology. So that helps me a lot to get my new job. So where I'm doing mostly the molecular biology and protein chemistry. So you will have a lot of opportunities when you start your PhD journey. It's tough and hard, but if you persistent throughout your 5 years, so it will be great.
That's good. So I'm sure our students also may have some questions, doubts. So this is the time for them to raise their voice.
Yeah, and one thing that's, I mean, even I'm pretty sure I never asked a question during my whole undergraduate life. uh, and one thing that you want to learn, because in here the students are forward that they will ask question, even though it doesn't matter whether you don't understand it.
Yeah.
Don't think that it will be a kind of, you know, someone will judge you depending on your question. So just ask. So that's one other thing that you guys need to learn in your undergraduate.
Students, now this is the time for you. Anyone?
Dr. Sriman, I have a sort of a general question. I've read that most of the clinical research that involves animal testing is sort of flawed, and I assume that's because of the anatomical and physiological differences between animals and humans. So my question is, in research work like yours, is it possible to use computational models or maybe neuromodulations or biophysical models instead of using animal testing? Or maybe do we have technology to use maybe some cell cultures instead of the whole animal? Do we have that sort of technology?
Yes. Good question. Yes, as I explained that we use mathematical models and many other groups use computational models too. So, but at the end, when it comes to approve a drug or a hypothesis to the before it prescribed to the humans, it need to go through the animals. The first we'll start with the lower order animals, and then you need to go for the primates, non-human primates like monkeys and everything. But using mathematical models of computational cell culture is really encouraged, because you can really reduce the amount of animals sacrificed for the research, because you don't have to do all the testing animals to get some information. Now the cell culture models, computational models are really advanced. So even what we're doing is we use as much as in vitro and computational models to get as much as more information we can get in the early stage of the research, and then get into the animal model, so which can reduce the animal sacrifice in the research. And the answer is yes, there are available technologies.
Thank you, Doctor.
More questions from the students? So don't get scared. He was also a student like you in 2009, I think.
Yeah, never asked a question. So take your chance and ask questions. It's a great asset for your life. So just
Excuse me, Dr. Srimal, I have kind of a question that is kind of related to your research. So like we know that when people have allergies, it's said to secrete more histamines in their bodies. So like, is there any correlation with that histamine and the histamine in the brain as a neurotransmitter? And if so, is there any like connection with them and like a patient with several allergies being prone to depression? Is there any kind of a relationship?
Good question. So the histamine, the peripheral histamine and the brain histamine levels are, it's not really connected. So because of the the blood-brain barrier, they regulate separately. So the only thing it would be is that if you take a drug for a peripheral to control the peripheral histamine levels, and then if that drug can cross the blood-brain barrier, so that could be an effect to the brain levels too. But it's regulated differently. And as I explained to Dr. Chandani Madam's question, so still there are research to understand the relationship between the brain levels and the peripheral systems like histamine, serotonin, dopamine. So then we can develop testing to detect the peripheral levels in order to relate with the brain levels. So far there is research is still going on that on towards that road, but we never find anything yet, but we will probably in the future. But it's a good active research in the field.
Thank you.
Doctor, I have a question that you told earlier that these immunosuppressive drugs, they are not equally acting on every person in the same way. So is there any method to develop these kind of drugs based on the individual genetic composition?
That is another active area of the research. So there are methods. So what some researchers do is that you can take your stem cells from the patients, and then you can generate the different types of cells from that. From stem cells, you can generate dopamine cells, serotonin cells, and there are in the latest research, you can find that you can make kind of a mini brains that consist of multiple neurons, and then you can test those neurons as a model of that particular the patient, and then develop therapies according to that. But it's active research and it's going on. So hopefully we will have that technology in near future, and it's a great area for research. Thank you.
Are there any more questions? Okay, in the absence of any more questions, I would like to invite Rini to give the vote of thanks.
Thank you, madam. Good evening, everybody. First and foremost, I convey my sincere gratitude to the guest speaker for today, Dr. Srimal Samaranayake, Research Assistant, Spark Therapeutics, Philadelphia, Pennsylvania, USA, for sparing his invaluable time for us to grace this occasion and enhancing our knowledge with a commendable lecture pertaining to novel perspectives on brain disorders with micro-engineered electrochemical detection platforms in spite of his busy schedules. Next, I'm sincerely grateful to the head of the Department of Chemistry and the patron of our society, Professor Manav Devi Vayu Ganahenige for the presence and immense guidance that always encouraged us. I also wish to express my humble gratitude to Dr. Tiloka Aryasena, the senior treasurer of our society, for mentoring us throughout, and without whose support and dedication, this event would not have been made possible. I'm especially thankful for all the other lecturers who graced this event and the demonstrators who were present. Finally, I heartily thank all the participants for their attendance. Thank you and have a good day.
Hello.